Previously, we have talked so many about the thermochemical equation, the definition for standard enthalpy change, and in this lesson, we will mainly focus on how can we really measure the standard enthalpy change in an experiment. And we will focus on two types of setups. The first one is to measure the standard enthalpy change for neutralization, and then for the second one is the standard enthalpy change for combustion. And no matter which standard enthalpy change we are talking about, we must need two informations. The first one is that you can consider the delta H as the molar energy. You can think in this way. What means by molar energy is that per mole of a substance form or per mole of a substance we add, okay, how many energy will be changed in the system. So that we have to measure two things. The first one is that the energy change of the system, and it is usually obtained by the energy change of the surrounding, because what we can measure is just the surrounding. And because of conservation of energy, these two, the energy change of the surrounding and the energy change of the system, they are equal in their magnitude if there is no any other types of energy loss. And however, their flow are opposite to each other. Say for example, if the system loses energy, then the surrounding will gain in energy. And on the contrary, then if the system increase in energy, it must gain energy from the surrounding. And the second data we need is the number of moles of a particular species. And say for example, for standard enthalpy change of neutralization, what we need is that we can measure the energy change first, and then according to the definition, what we need is the number of moles of water, so that for the molarity of the reagent used, we must know, and then their volume used must be also measured precisely, so that we can, by using of mv equal to number of moles and then the corresponding mole ratio between the acid and alkali and water, and then we can find the number of moles of water, and we got all the information we need through this. Let's go into the detail about the setup used, and just very easy. The setup we use is, say for example, if we have a small beaker, 100 ml beaker, or you can use expanded polystyrene cup in here, and then surround this small beaker by some cotton wool. And you can think of why each of these material are used in our setup. And finally, put the whole thing inside a large beaker, a 600 ml beaker. And then finally, the reaction mixture will be inside this small beaker. And then we add a lid on the top. And then add a thermometer. And in case you have it, you can use a stirrer to mix the solution well. And that's all for the setup. Oh, no, never mind, just add back those. And here is all for the setup. So there are several things we need to know their functions. What are the use of the cotton wool and also the lead. Of course, the cotton wool, it can trap air, which is a good insulator of heat, so that it can help preventing heat loss to the surrounding, and it is also the function for the lead. And both of these are used to prevent heat loss or heat gain from the surrounding, or for simplicity, we can just write down to prevent the heat transfer with the surrounding. And if it is an exothermic process, and we prevent heat loss. If it is an endothermic process, we have to do the reverse to prevent heat gained from the surrounding. So can you see the idea? Oh, and then the second thing is that what is the use of the thermometer. There are two things we need to two kinds of data we need. First of all is the number of moles, and then the second one is the energy. What is the use of the thermometer? To obtain the temperature value. Is it okay? And then we can apply the equation later on, mc delta T, to calculate the energy involved in the process, so that we must need thermometer to measure the temperature. And then the stopwatch is to measure the time used in the experiment. Because later on we will do some data analysis by drawing a graph of plotting temperature against time. Oh, and here is my data set. And because I record several data with different time as stated in the menu, so starting from here, 180 seconds and between 240 seconds, the data set is a little bit different for the time data. Maybe I give you some time to copy this data in case you do not have yours. And then we will do the analysis by plotting temperature against time. So let's move forward. Oh, first of all, the first skills to draw this kind of graph is that you have to maximize the use of the scale. So for example, the paper is like this. Of course, here is the origin on the bottom left corner. And then our maximum reading is just around 30 something. So each of these square can represent 0.5 degrees Celsius. So the scaling is like this. Try to maximize the use of the scale. And then the vertical axis should refer to the temperature. So just draw the axis. And here's the temperature in degrees Celsius. Oh, and then similarly for the horizontal axis, we use time second. And then because the maximum reading is 600, so therefore each of the small square can represent 6. So the first data it should be 30, 60, and then just the multiples of 30. Let's continue first. And then again draw the axis. Oh, after drawing this, then you can copy the data onto this graph. Oh, and in chemistry, for drawing the data, we usually use a cross to represent the data. So 0 second, 30 second, and then to 50. To 150. The data are 25.2, and then at this 180 second is the moment at which we add the solution into the exit. And after that 185, 28.8, and just continue to plot the data points. Oh, and the data set is roughly like this. And what we have to do next is that we have to simulate the situation that there is no any energy loss to the surrounding. Say for example, in this case, starting from maybe this point, 240 seconds, then you can see that there is a small drops in the temperature from 31.5 to 31.2. And the story is that during the addition of the reagent and during the reaction and after the reaction, because the reaction mixture has a higher temperature than the surrounding, so that there will be some heat loss to the surrounding. And it means that if we just use this 31.5 data, is actually not the maximum temperature the system can get. It's because some heat has been lost to the surrounding. And by assuming that the rate of heat loss to the surrounding is a constant throughout the experiment, we can extrapolate the line. 我哋可以延長翻條線啦 back to the moment that we add the reaction mixture together. And then we can generate, if there is no any heat loss to the surrounding, what will the maximum temperature the system can get. Can you see the idea? So that just using a ruler and then try to extrapolate this decreasing trend. I'm not able to draw a straight line in the PDF file, so that I use another app to illustrate you how to draw that extrapolation line, and this just look like this. Okay, because there is a decreasing trend, okay, so that we just draw somehow like a best fit line and then passing through the maximum data point, and there is 31.5. And you can see that if we extrapolate this data point back to 180 seconds, then the temperature is slightly higher than that 31.5. Well, and according to the analysis, the value of it is 31.7 degrees Celsius. And then because the initial reading is just a constant value, so that we just extrapolate it and then to 180 seconds similarly, and then get the value 25.2 degrees Celsius. And then the temperature change is the difference between these two values. And this should be 6.5 degrees Celsius. Oh, and go back to your note, the maximum temperature rise X obtained in the diagram is 6.5 degrees Celsius, is the temperature change. Oh, and then if we can apply the mc delta T, then we just plug into the number, and in this equation m is the mass of the solution, and because totally we are using 25 ml and then 25 ml of NaOH and HCl respectively, so that the total volume is 50 ml, 50 cm cube. And then given by the question, the density of the solution is assumed to be 1 gram per cm cube, so that the solution, the mass of it should be 50 gram. Oh, and then the specific heat capacity as given is 4.2 joule per gram per Kelvin. Oh, and then finally for the delta T is 6.5. And then because the difference between 2 degree of Kelvin scale and degree Celsius are the same, so that the difference of 6.5 degrees Celsius is just equal to 6.5 K. And you can see that some of the units, they can be cancelled out. The gram, and then gram to the power -1, Kelvin to the power -1, and then Kelvin. What's left is just joule. And then just use your calculator to help you. To remind you that the standard enthalpy change of neutralization, we usually use kilojoule per mole as the data, so that the energy release, if we convert into kilojoule, it should be divided term by 1,000, and it is the energy released during neutralization. Oh, and then the next thing is that you have to calculate the number of moles of water, and here is the balance equation for NaOH. We have with 1 HCl to form NaCl and then water. And for HCl is 25 ml 1 m, and also for NaOH. So that none of them is in excess or limiting, you can use either of these two species to do the mole calculation. And for water, because the mole ratio is just 1 to 1, so that we just use MV. And then times the mole ratio, and then the number of moles of water formed is 0.025 mole. Well, now you have the energy data, and then you have the number of moles of water. You can plug into the equation, and the standard enthalpy change of neutralization equal to negative 1.365 divided by 0.025, and the final answer is 54.6 negative kilojoule per mole. And the reason why we have to add this minus sign is because for the top one, this is the energy release to the surrounding. So if you draw out the energy profile, it looks like this. Originally is the reactant, and then the product, it has a lower energy level, and there will be of course a decrease in the enthalpy level, so that the enthalpy change is a negative value, and then this amount of energy will goes to the surrounding, and this is the energy release. So that we must add back this negative sign to present the idea that, oh, in the product side is a more stable species, and it is an exothermic process, and it is releasing heat to the surrounding. Can you get the idea? Oh, and then the second part of this experiment is to see the neutralization of another acid with NaOH, to see if we can get the similar result or a different result. And this time we will use ethanoic acid, a weak acid, to react with NaOH, and the corresponding data is like this. Plot it first by yourself, and then to see if your result match mine. Oh, let's move on. And then similarly, you can get a graph somehow like this. The vertical axis, temperature; the horizontal x-axis, time per second, and then just the data points. Yeah, is it okay? Then again, do the analysis by another apps first. And then for the analysis part is just similar. For the initial temperature part, because now it is an upward trend, so that we again draw somehow like a best fit line to extrapolate it to 180 seconds, and then also for the decreasing trend. Well, for the first one, for the initial temperature, it should be 23.5 degrees Celsius. And then for the final reading is roughly equal to 29.2 or 0.3. And then you just do the subtraction, and this time delta T equal to, and then equal to 5.7 degrees Celsius. And I can draw it better for you. The delta T should be this range, delta T. Oh, and then after you have the delta T term, which is equal to 5.7, then you can put it in the MC delta T, and this is the energy absorbed by the surrounding. And M again is the total volume of the solution times the density, and it is 50 gram because again 25 cm cube of the solutions are used respectively, 25 plus 25. And then the C just 4.20 joule gram to the power -1 and K to the power -1. And then finally the delta T equals to 5.7 Kelvin. When again time for the calculator, and this time equals to 1.197 kilojoule. And I already divided the answer by 1000 to convert it into kilojoule as a unit. Okay, and then for the reaction between CH3COOH, the Ivanova acid, and NaOH, again the equation is a 1:1 ratio equation. So the number of moles of water equals to mv times 1, that is the mole ratio. M is 125 divided by 1000, and mole ratio 1:1, and finally again 0.025 mole. Oh, and then by finishing it using the definition, delta H of neutralization equal to the enthalpy change per mole of water formed. And don't forget this negative sign to present the idea that the heat is losing to the surrounding from the system. And then the final answer is negative 47.9 kilojoule per mole. Is it okay? Well, although in these two experimental results they are not similar because maybe some experimental error, but in fact you can get the similar number if you perform it well. It's roughly equal to negative 50 kilojoule per mole. And if you write down the equation for this, the ionic equation of these two reactions, it will be like this. For sodium hydroxide, it provides the hydroxide ion, and then the acid, it provides the H+. And then the ionic equation for both processes is just H plus AQ plus OH minus AQ to form water, because their reactions are actually the same, so that the enthalpy change, the value should be the same. However, for Ivanova acid, it gives you a less negative value, and you can just link it to the definition of a weak acid. What means by a weak acid? Well, a weak acid is only partly ionized to form hydrogen ion when dissolved in water, and some of the energy in the process is actually used to ionize the H plus before reaction can take place. Can you see the idea? So the energy released to the surrounding will be relatively less than that between HCl and NaOH. And that's all for the measurement for standard enthalpy change of neutralization. Oh, and then go to another measurement, and I won't show you, and I think you can grab the same idea after I draw the setup for you. And again, we use this apparatus calorimeter, and the term calorimeter, calorie means calorie, is something related to energy, is a unit for energy, and the calorimeter is the setup for measuring the energy released from a reaction. Or absorb, of course. Oh, and then the second types of reaction we would like to do the measurement is combustion. And combustion is again, is it endothermic or exothermic? Or it is again exothermic. So how can we apply the same idea? Again, we have to use MC delta T to do the calculation. Then how can we construct a setup? So for example, if there is a spirit burner, 酒精燈, and then you would like to burn some fuel inside and some fire. How can you measure the heat release? By using water. Or we just use it to boil, to heat up some water, and then on the top, this time we will use a metal can. Why a metal can is used instead of maybe a beaker or a polystyrene cup? Well, because it is a better conductor of heat, and then it can more effectively transfer the heat into the water inside. Fixed amount of water. And remember that do not use any cotton wool to surround this metal can. Otherwise, those cotton wool is not helping you to prevent heat loss to the surrounding. Instead, it will catch fire. Is it okay? However, we can still add a lid to prevent heat loss to the surrounding. And then we have to measure the temperature by a thermometer. And then what's more is that we can add to maybe plastic screen to help you to minimize heat loss. And you see the whole idea. However, you cannot put it in a closed system. It's because for the definition for standard heat of combustion is that the enthalpy change when a mole of a substance undergo complete combustion in oxygen under standard condition. If we do it in a closed system, then it may undergo incomplete combustion. Is it okay? So that it will not fit the definition for standard enthalpy change of combustion. And of course, you can again add some stirrer, help you to make the heat more evenly distributed. Oh, and the idea part I told you already is that because the combustion is an exothermic process and the delta H is negative, so that if they are burnt in this spirit burner, it will generate some heat. And then where will those heat goes to? It cannot be created nor destroyed, so that it must be transmitted into another form or transit from place to place. Now it will through these metal cans and then to the water. Is it okay? And then the water will be heated up, and then if you again apply the formula mc delta T, you can calculate the energy absorbed by water, and then if you calculate the number of moles of the fuel used, then you can get the data. Oh, and of course, this case, the water will absorb the energy, and then the water will increase in temperature. And for the use of a metal can is a good good conductor of heat, so that the whole process will be more efficient. And then the use of longer amount of water, because we have to use mc delta T, this equation. And if we want it more detailedly, it will be mass of water times the specific heat capacity of water, and then the change in temperature of water. So if we do not know the mass of water, then we cannot apply this equation, then we can get nothing. Okay. And then the plastic screen and then the lid is to prevent heat loss to the surrounding. I tell you already why we can't do it in a closed system. If it is the case, what will happen? Only incomplete combustion occur. To make the experiment not suitable for measuring the standard enthalpy change of combustion, in which complete combustion is listed. Well, before going to answer the next questions, I'll go through some procedure first. And I think you get the idea why we can use the calorimeter in the measurement. And if you are really doing this experiment, what you have to do is, of course, to construct this setup, and then before the burning the fuel, we measure the initial total mass first. Mass of the container, mass of the spirit burner plus the fuel, and we consider it is M initial. And then M final is to measure the mass of the burner, the total mass of the burner, plus the fuel after reaction. Is it okay? And then if we have these two data, we just use M initial subtracted by mass final is actually the mass of the fuel used. Well, and then time to talk about the equation. Oh, in case you want to calculate the standard enthalpy change of combustion, of course you need the energy change of the system, and then divided by the number of moles of the fuel used. It's because standard enthalpy change of combustion is the enthalpy change when 1 mole of the fuel, 1 mole of a substance is burned completely in oxygen under standard condition. So what you have to do is to divide the energy by the number of moles of the fuel used. Then you can calculate the number of moles of the fuel used by using mass over molar mass. And then for the delta H, we just keep it the same first. Energy, we can use negative mc delta T to calculate the change in the surrounding, and then add back the negative sign to represent the energy change of the system. And then finally, in the bottom one, we can use mass over molar mass to calculate the number of moles of the fuels. And the question is that after the rearrangement, we get this equation. Then can these two mass be cancelled out? Well, the answer is obviously not. In the mc delta T equation, what means by the M? Well, it's mass of water, is it? And then for the later one, in the mass over molar mass term, what is the mass referred to? Or it refers to the mass of the fuel. Is it okay? So that if we write down a clearer version of the equation, it will look like this: mass of water times specific capacity of water delta T of water divided by delta HC equal to mass of the fuel divided by molar mass of the fuel. So these two masses cannot be cancelled out. And then in the experiment, I tell you already what measurement you need to take: the initial mass of the fuel and the spirit burner, final mass of the spirit burner and the fuel, and then the initial temperature and final temperature of water. And then for the procedure part, and I think you can handle it yourself. Oh, and here is roughly how does the procedure look like, and you just plug into the corresponding side, you can get the result. So for example, for this T final and T initial is actually for calculating the delta T of water, and then for the mass of the fuel used is just equal to M initial minus M final. And then you, by use just the equation, you can calculate the standard enthalpy change of combustion already. Oh, and in the setup there are mainly two areas. The first one is that heat lost to the surrounding, and the second thing is that incomplete combustion may occur. It will also alter the result. And also in the setup there may be some of the things they will also absorb the heat. Say for example the metal can, the plastic screen, the thermometer, they will also absorb some kind of heat. So it may lead to some error. Oh, and that's all for the setup part for direct measurement. And let's try one examples together. Oh, in this case, for the reaction between zinc powder and put it inside some silver nitrate solution, and obviously it should be an displacement reaction, and again it is an exothermic reaction. And part A, easy, right? Zinc react with 2 AgNO3 to form zinc nitrate and 2 silver metal. Calculate the number of moles of silver nitrate first. And we just use MV, M times V, and the number of moles of zinc equal to 1 times 50 divided by 1000, and then the mole ratio. And the reason why we have to calculate the number of moles of zinc is that the reaction, we write it like this, and the corresponding delta HR is to be referred to 1 mole equivalent of this equation occurs, so that we use zinc as the main character, then we can make the calculation more simple. Oh, and the next thing is that you have to apply the energy change of the system by MC delta T. And I directly calculate the system, the energy change of the system, and it will be equal to negative MC delta T. And then as you may see in the specific heat capacity term, we use kilojoule and then kg as a unit for mass, and then Kelvin as a unit for temperature. So that for the first term, you have to divide it in order to convert it into kg, so that the units can be cancelled out. First of all, K can be cancelled out, and then kilogram can be cancelled out. Only F is the kilojoule term. Oh, and finally, the delta HR will be just equal to this energy per mole of zinc reacted. It means per mole of this equation reacted. Is it okay? So that we directly divide it by the number of moles of zinc. Yeah, and it is negative 359 kilojoule per mole, or more precisely